All right, in this video we're going to be looking, in the chapter of nuclear chemistry, and we'll be looking a little bit more at stable nuclei and what makes a nuclei stable and what's actually holding the nucleus together. So that's kind of where we're going, and so we're going to have to talk about a couple different forces at play. And our question is, why do some nuclei undergo spontaneous decay while others don't? Okay, not all nuclei are radioactive, and so what is holding the nucleus together for these ones that are very stable, and what is going on when they're not very stable? All right, so a couple different forces going on that we have to pay attention to. We have the electrostatic force, all right, and this force is the one where you would say that opposite charges will attract and like charges repel. And we've talked about this before when we've talked about binding and when we've talked about bonding going on. So we have I guess with an ionic compound, for example, we have a positive cation and a negatively charged anion, and we have that electrostatic force interaction, okay, forming that ionic bond between the positive and the negative. But we also know that like charges will also repel each other, okay? So you have opposite charges attracting, like forces will now repel. Well, what is in the nucleus again? Okay, what do we have in there? We have in the nucleus, we have protons and the neutrons. Now the neutrons have no charge, but our protons have a positive charge. Well, if we're just thinking about this electrostatic force, we would assume that all nuclei would probably be unstable because we have these positive protons all kind of repelling each other. All right, so we have this force kind of keeping it apart, but we know that a lot of nuclei are stable. So we have this other force at play, and this we call the nuclear strong force. Now, this force, I would say, you probably want to start. This is a very, very strong force. And this force acts on a short range, and this is attraction between pairs of nucleons. So protons and neutrons, neutrons and neutrons, neutrons, protons, protons, neutrons, neutrons, protons, neutrons. I think I got them all. And so these are kind of at play here. When this one goes on, and the textbook that we use is kind of a silly book in general when some of these cartoonish pictures go up, but you know, some of them actually help get the picture. You can see the protons are not very happy, they're going to repel, but this neutron is kind of acting like a glue holding the nuclei together. All right, so when you have the strong force greater than the electrostatic force, you will have a stable nuclei. All right, so this stable nuclei will not decay, okay, spontaneously, but an unstable one would decay spontaneously. All right, so if you have the electrostatic force greater than the strong force, this would lead to something that would be unstable, and it would undergo spontaneous radioactive decay. And this unstable nuclei would undergo this radioactive decay until it reaches a more stable nuclei. So its goal then is to become more stable. All right, so those are kind of the forces involved here that we're looking at. And there's a couple trends that we can see. So if we make a graph, and this is the graph of the number of neutrons versus the number of protons. All right, and so just to kind of show, you have over here number of neutrons and the number of protons. You can kind of see, okay, so proton divided by neutrons, the line in red is when it's equal to 1. And it has been found, okay, they have put on this graph where the stable nuclei, their neutron to proton ratio is. So the principal factor in nucleus stability is this ratio between the neutrons and the protons. So scientists have now figured out, okay, for all these known isotopes, all the stable ones will lie within this band of stability here, okay? So this includes the radioactive stable ones and the non-radioactive isotopes. And they are all within this band of stability. And one thing to note, okay, so a couple things here to note, but first thing, when you have the atomic number equal or less than 20, they all lie right on this red line, okay? So this is a 1-to-1 ratio of neutrons to protons. So they're, for small or light elements, a 1-to-1 ratio is more stable than not a 1-to-1 ratio. As the atomic number gets larger, okay, more mass, more neutrons need to be present than protons. So you can see now that there are more neutrons compared to protons. So this ratio is not 1-to-1, now it's more like 1.25, 1.33 to 1 as you go up in the number of protons. So the N to P ratio increases, and so it's more stable as you need more neutrons for all these extra protons you have. So the more protons, the more repulsions you have, the more neutron glue is needed. And so when you have atomic numbers greater than 20, now this ratio is higher than a 1-to-1 ratio. All right, that was that one. Let's now look at an example. I want you to actually be able to do a calculation here to make sure you can calculate this ratio. So let's see, can you find the ratio, the N to P ratio, okay? And how you do this is you find the number of neutrons and the number of protons and divide and see if it fits on that band of stability. So I want you to do this for both carbon-12 and carbon-14. Find the N to P ratio for both of those, and then tell me which one would you predict to be the most stable. So pause, take a break, get your work done, and then come back. All right, hopefully you have got this figured out as well. I wrote down the two isotopes here, carbon-12 and carbon-14, and let's calculate the N to P ratio. Hopefully you did it as well. When you have 6 protons, the mass number is protons and neutrons, so 12 minus 6 is 6. We have 6 divided by 6, and this would be a 1-to-1 ratio. So we have a N to P ratio of a 1-to-1 here in this case. All right, the other one, now we have a mass number of 14, so this has 8 divided by 6, all right, and this is 1.33 for our ratio here of neutrons to protons. Now, since carbon-12 is a fairly light, it's under 20, atomic number is under 20 here, we would expect the most stable isotope to be the one with a 1-to-1 ratio, which in this case would be our carbon-12. Since it's a 1-to-1 ratio, more stable. All right, so let's now do a little bit more check and some calculations. We're going to now look at calculating some of the stability, looking at the binding energy. All right, so if you add up the mass of the protons, neutrons, and electrons, you do not get the experimental or the calculated mass of the nuclide. There is some mass missing between what you expect if you add up the protons, neutrons, and electrons and what you actually get. All right, this mass loss is converted to energy and released when 1 mole of the atoms are formed from the subatomic particles. And we call this the nuclear binding energy. All right, so nuclear binding energy. I just said this is the energy loss when and converted to energy when 1 mole of the atoms are formed from its subatomic particles. This would also be that same energy needed to break up a nucleus. So it's the energy that's released when it's formed or the energy required when you break it up. All right, so same thing there. It's either required or formed. The larger the binding energy, the more stable the nucleus is. Okay, the more energy holding it together, the more energy it would have to take, or more energy before you can break it apart, so it's going to be more stable. All right, and then let's see. We're going to talk about now this energy and how we can calculate it. And this is using Einstein's equation, E equals mc squared. Let's talk about what these things mean. E is energy. And when we do the calculation, it's going to be in kilograms times meters squared over seconds squared when we get it all worked out. I just want to make a note to you that that is the same unit as a joule. So when you see that I go from kilograms, meters squared per second squared, and I just write a joule, that is why it's the same thing there. Now the M here, this is called our mass defect. And this is that mass that was lost, okay? We said that all of the mass, if you added up the protons and the neutrons and the electrons, is larger than the actual mass of the nuclide. And that mass difference there is the mass defect. And this is the mass that was lost when it came together and was converted to energy. When we do this, we often will do it in kilograms. We'll get it to kilograms so it can go into our equation and solve for joules. So we'll get it into kilograms, and it's often per mole. And then C, we know that's a constant, the speed of light. And that is 3.00 times 10 to the 8th meters per second. And so that's going to get squared. That's where you get the meters squared per second squared. And then the mass defect gives us the mass in kilograms, which those units all combined then give us joules for energy. All right, let's actually try a problem and see if we can work out an example. So I want you to calculate the mass defect first for 1 mole of carbon-13. And I'm telling you what the actual mass of 1 mole of carbon-13 is, and it's 13.00335 grams. Sorry, I'm going to be using lots of sig figs here. So we first want to calculate, okay, if we just added up what a carbon-13 atom is made up of, the protons, neutrons, and electrons, what mass should we get for 1 mole? All right, so we know in carbon-13, we'll write it out like this, and its atomic number for carbon is 6, that this has 6 protons, and it has 6 electrons, and we have 7 neutrons. How did I get 7 neutrons? What numbers did I do there? I took the mass number, which was 13, which is protons plus neutrons, and I subtracted the protons. Protons I found from the periodic table, right? That's the atomic number, and then I found that 13 minus 6 is 7, so there's 7 neutrons. All right, now you would be given the mass of a proton, neutron, and electron, and I'm going to tell you that sometimes the mass of the electron, since it's so small compared to the proton and the neutron, sometimes it's left out even. So, but we'll do it with it here in this example. So starting with 6, and we're trying to do this for the mass of 1 mole of carbon-13. So 1 mole of carbon-13 would have 6 moles of protons. And we know that the mole of a proton, this would be given to you. So 1 mole of a proton, and this is 1.00730 grams. So adding up all the not the proteins, the protons, you would get 6.04380 grams. Sorry, we are keeping lots of sig figs. All right, do the same thing now for the neutrons. There's 7 moles of neutrons. The mass of a neutron is very close to the mass of a proton, just a little bit bigger, 1.00870 grams for every 1 mole of neutrons. And so this gives me 7.06090 grams. And lastly, we're going to do the electrons in this case. So we have 6 moles of electrons. Mass of electron is very small, and it is 0.00055. I hope I can read my handwriting good enough. I think that's what that is, 55 grams. All right, and when I calculated that, I got 0.0033 grams. All right, add those 3 up. Okay, that is your mass from 1 mole of protons, 1 mole of the neutrons, and 1 mole in carbon-13 of electrons. All right, so all the protons, neutrons, and electrons, and I got 13.1080 grams. All right, so this number is bigger, right? We're comparing this number right here and this number over here. It is bigger than the actual calculated mass of a 1 mole of carbon-13 atoms. And so the mass defect then is just the difference between there. So mass defect would then be, take the bigger one, 13.1080 grams minus your 13.00335 grams. And I got a difference of 0.10465 grams, and this is the mass missing per mole of carbon-13. All right, so we need that mass defect to now plug in to say, all right, if this mass is now converted to energy, how much energy is holding this nucleus together? And the higher that binding energy, or the energy holding the nucleus together, the more stable it is. All right, so we're going to use the E equals, I might just change color just to give us a little bit of a change here and to help you follow what I'm doing next. So E equals mc squared. Now, I told you that in order for us to get to units of joule, we needed to get our mass into kilograms. So I'm going to do that at the same time here. So if you're following along, we're going to start with our mass given in grams. 0.10465 grams for every mole here. So this is per mole, and I'm going to convert this just to kilograms. That's our simple conversion. In 1 kilogram, there are 1,000 grams. All right, and that's the M part right here. We'll just kind of keep that separate. Now we're going to do the C squared part. So our speed of light is 3.00 times 10 to the 8th. Units on that are meters per second, and this is squared. So this will now be meter squared per second squared. Get your calculators out. Solve along with me. When you plug in this, I ended up getting, let's see, I think I got 9.42 times 10 to the 12th. I should always double check my math. Times 10 to the 12th, I think. And this is kilograms, meter squared per second squared, which is the same thing as a joule. All right, so it's 9.42 times 10 to the 12th joules. And let's just get this into kilojoules because that's oftentimes how it's expressed. So if you want to go between joules and kilojoules, you know that in 1 kilojoule there are 1,000 joules, and that then leads us to 9.42 times 10 to the 9th kilojoules, and this is all per mole of carbon-13. All right, we did a great job finding the binding energy. Often though, if you're trying to compare binding energies, you want to compare them per nucleon and not just per atom, because they have different number of nucleons. So like a carbon-12 versus a carbon-13 versus a carbon-14 have different number of nucleons. And so in order to compare their binding energy to figure out which one's more stable, you'd want to take this divided by the total number of nucleons. All right, so if you have carbon-13, how many nucleons does it have? Since this is protons plus neutrons, this is 13. All right, so take our number that we just got, 9.42 times 10 to the 9th kilojoules per mole, and then you're dividing by 13 nucleons, and you get 7.25 times 10 to the 8th kilojoules of binding energy per mole of nucleons. I'm sorry, this is writing really small, but per mole of nucleons. All right, that is a lot of information. We will do another one of these as a practice in a little bit, but just to kind of show you, the amount of energy that's given off here from a nuclear reaction is huge compared to the amount of energy in a chemical reaction. All right, this is a very large number. We are able to then look at, okay, there's another graph here just to show you. This is showing the binding energies, okay? So over here, we have binding energy per mole of nucleons for different isotopes. These are known stable isotopes, divided by the number of nucleons in their nucleus. Okay, whew, it's a mouthful. And you can see kind of some trends here. Here's carbon-13. All right, we just calculated that to be, what did we just calculate it to be? 7 point something. And you can see that, kilojoules. And then here's carbon-12, okay? And we said carbon-12 is more stable already because it has that 1-to-1 ratio. And you can see that's higher up here, has higher binding energy. So this is kind of helpful thing. I want to just make sure you can see what isotope out of all of here would you say is the most stable isotope of all of the elements? So using this binding energy graph, can you pick out which one is the most stable? Most stable equals highest nuclear binding energy. All right, so looking here, binding energy, the highest one, that's this one right here. That is this iron, isotope of iron with 56 nucleons. And since it says the highest binding energy per mole of nucleons, that's your most stable isotope of all the elements. Next slide is going to be another video kind of working through another example of nuclear binding energy.